Welcome back to the deep dive. This is where we take a whole stack of sources, research, notes, all sorts of things, and we try to boil them down to the really essential, sometimes surprising bits of knowledge just for you. Today we're diving into something well, it's everywhere in our lives, but we almost never think about it. The incredible story of how we figured out how to control the climate inside our buildings. Okay, let's unpack this. We're talking heating, ventilation, and air conditioning, HVAC. It really is the unsung hero of modern life. Like a foundational thing that has literally reshaped where we live, how we work. I mean, just think about it for a second. Without good climate control, huge parts of the world, they'd be much, much tougher to live in. And modern buildings, skyscrapers, big suburban houses, they just wouldn't exist the way we know them. HVAC let us conquer heat, cold, humidity. It totally changed how humans experience indoor space.
Yeah, and what's fascinating here is this human need for, thermal comfort. It's not new, not at all. It's ancient. It's been a really deep driver in how we design buildings for, well, forever. For millennia, people have tried to make spaces that protect them from the elements, whether that's, brutal desert sun or freezing northern winters or sticky tropical humidity. And the sources we've looked at for today, they give this really unique perspective, focusing specifically on the building side of things, how the structures themselves evolved from those really early intuitive designs right up to the super engineered environments we have now. So the journey we're taking today is going to cover a lot of ground. We'll start with those early, often passive ways people tried to control climate, built right into the architecture. Then we'll trace the big steps in material science, engineering breakthroughs, the stuff that made mechanical systems possible. And finally, we'll jump to today. Smart systems, energy concerns, digital integration, the whole 9 yards. It's really a story about human ingenuity constantly adapting to stay comfortable.
It really makes you wonder, though, doesn't it? Before all the complex machines, before electricity, fancy thermodynamics, how did people even start trying to make inside spaces comfortable? Where did this whole quest begin? How on earth did they manage?
That's exactly the right place to start. Our ancestors, they didn't have thermostats, sure, but they understood their environment. Maybe with an intimacy we've kind of lost, sitting in our perfectly controlled boxes.
Yeah.
Their solutions were often, well, elegant, simple, but deeply integrated into the buildings themselves.
Yeah, they were incredibly clever. Long before complex machines, they were using the architecture, the building itself, to manage the climate inside. It wasn't just about basic shelter, right? It was about getting some comfort right from the start, just using what they had available.
Absolutely. And when you look at, say, classical architectural texts, you examine old structures, you see it immediately. Ancient builders, even without our modern HVAC, they just got basic environmental principles. Like take Andrea Palladio, his famous 4 books of architecture from the 16th century. It's full of these incredibly detailed insights into how specific architectural choices affected the building's internal climate. It's like a masterclass in early passive design. He spent a lot of time thinking about the most beautiful and proportionable manners of rooms. He talks about whether they should be round, square, or have these really specific rectangular ratios, 1 square and a third, 1 square and a half, even 2 squares.
Ratios, like mathematical ratios for rooms.
Yeah, exactly. And these probably weren't just about making things look nice, visual harmony.
Mm-hmm.
Think about a round room. It has less surface area for its volume compared to a long rectangle, right?
Uh-huh. Less wall space.
Right. So that could mean it holds heat better in a cold Venetian winter. Or maybe, if it was designed for cross-ventilation, it could dissipate heat more evenly. A rectangular room, though, with those longer walls, has more potential for sun hitting it or losing heat. So Palladio, he wasn't just sketching nice rooms. He was, in a way, intuitively engineering the thermal performance, thinking about how geometry itself affects comfort and energy. Long before computers could simulate it. It was based on generations of, just seeing what worked.
That's a really deep level of thinking, down to the basic shape of the space, not just looks, not just structure, but how it performs environmentally. That's quite holistic for back then.
Exactly. And he didn't stop there. He goes into detail about pavements and ceilings. He mentions floors made of terrazzo or bricks or live stones. But the really telling part, the detail that often gets missed, is his advice that these floors should be made in spring or in summer, that they may be well dried.
Oh, why? Just so they set properly.
Well, yes, partly structural integrity, but it also suggests a really deep practical understanding of materials, how they interact with temperature, with moisture, how much water is left in the material matters for its long-term performance, its durability, and crucially for us, its thermal properties. You wouldn't want a damp floor constantly feeling cold underfoot, or adding humidity to the room, right? Or slowly degrading the structure over time. It shows an early grasp of what we now call hygroscopicity, how materials absorb and release moisture.
So they were thinking about material science, even without the fancy terms, to manage dampness and temperature.
Oh, wow. Okay, here's where it gets really interesting for me. Palladio also talks about designing these grand spaces like the Corinthian atrio or halls with four columns, tetrastili he calls them, and specific vaulted ceilings like a semicircle or a schifo. What's a schifo?
A schifo vault. It's a type of vault where two opposite sides curve inwards, meeting at a ridge along the top, kind of like a barrel vault, but pinched in the middle. Okay, got it. So how would these fancy shapes, these vaults and atriums, affect the climate inside these big palaces?
Oh, hugely. They'd influence both air movement and thermal mass. A high vaulted ceiling, for instance, hot air rises, right? So it allows that warm, stale air to gather way up high, leaving a cooler zone down where people actually are, especially good in warmer climates. The shape itself helps stratify the air, helps natural convection currents. It's basically passive ventilation by design. An atrio, often in the center of the house, that open space could create really effective cross-ventilation, pulling air through the whole building, like the lungs of the house. And that schifo vault. Its curved surfaces create a large volume, promoting air movement, preventing stagnant air pockets. The curves might even diffuse light and heat in specific ways. And even more directly, Palladio gives detailed advice on aspects, the orientation of buildings, for temples, for houses. He refers back to the principles he laid out earlier about how to align buildings on their sites to deliberately use or block things like sunlight and wind.
So pointing the building the right way.
Precisely. And you see it in practice in his designs for these Venetian country houses. The main living area for the owner is central, but the stables and cellars, they're put on the sides.
Is there a reason for that placement?
Absolutely functional. Those stables, animals generate heat. They could act as a buffer zone, maybe warming the nearby living spaces a bit in winter. And cellars, naturally cool, provide passive cooling in summer. These support buildings weren't just separate. They were integrated climate modifiers, shielding the main house and helping moderate its temperature.
So the building itself, its orientation, its geometry, its materials, that was the HVAC system, basically. These passive ideas weren't add-ons. They were baked into the design. That's really sophisticated thinking.
Exactly. Materials and form were the main tools. And this kind of intuitive knowledge wasn't just for grand villas. You see the same principles echoed in modern building science texts like Building Construction Illustrated or How Buildings Learn. They talk about window orientation, for example. It's critical. South-facing windows can be effectively shaded in summer, but let in sun in winter, balancing heat and light. North-facing windows are exposed to winter winds, so they lose a lot of heat.
And east and west.
Tricky ones. East and west-facing windows are sources of overheating and are difficult to shade effectively. That low morning and afternoon sun angle is hard to block, leading to unwanted heat gain. Architects constantly wrestled with that. And roofs, often overlooked but so important. Pitched roofs, the benefits go way beyond just shedding rain. They provide a volume of air under the roof that absorbs radiant heat and water vapor and vents them to the outside.
Like an attic space.
Exactly. That attic creates a crucial buffer zone. It intercepts the sun's heat, lets it vent out, keeping the rooms below much cooler, and it manages moisture. Plus, pitched roofs can have eaves that overhang enough to protect the walls from rain and sun.
Oh, right. Overhangs keep the sun off the walls, too.
Yep, prevents direct solar gain on the walls, minimizes rain hitting them. It's just a master class in passive climate control, all integrated into one design feature.
That's a lot of work for just a roof, doing multiple jobs at once. What about something simple, like roof color? Does that make a difference, especially where it's hot?
Oh, absolutely. It's a brilliant, simple example of passive design. The source points out how important roof color is. A white or silvered roof reflecting away the sun's heat and destructive ultraviolet rays, the building will be far more comfortable and energy efficient.
Just reflecting the heat away.
Simple as that, but incredibly effective. Think about the difference that makes in a building without AC. Every degree of passive cooling you can get matters. It dramatically reduces the heat load getting into the building. And we even find surprisingly early examples of complex ventilation. Maybe not for comfort as we think of it, but for basic survival and safety. George Agricola's Dairy Metallica from way back in 1556.
What about mining, right?
Yes, metallurgy and mining. He describes how miners dealt with airflow in deep shafts and tunnels. They had to get rid of dangerous gases and bring in fresh air. He talks about air blowing into an upper shaft or tunnel, now into a lower one. It shows they were deliberately trying to move air. It's a basic understanding of moving air to make a space habitable, even if it wasn't about achieving a perfect 72 degrees. It laid some conceptual groundwork, you could say, for later ideas about moving air for comfort.
It's just incredible to think how hard it must have been to get any real comfort or even safety without machines. These passive designs orienting a building just right, placing rooms strategically, the roof shape, the color, they weren't just decorative, they were about survival, about making life workable. They led to very specific building forms tied directly to their environment. They were the original HVAC engineers, in a way.
They really were. And those early choices, those subtle design features, they absolutely laid the groundwork. They influenced how we later thought about more complex, active systems. Principles of thermal mass, orientation, natural ventilation, they're still fundamental to cutting-edge sustainable design today. It's a good reminder, sometimes the oldest ideas are the best solutions for our current energy problems.
Building on that, then, our understanding of the materials themselves took a big leap forward. That allowed for much more precise control over the indoor environment. It feels like we started to almost micro-engineer the building's skin, turning it into a more finely tuned instrument.
Yet we connect this to the bigger picture. The basic properties of building materials. They're constantly interacting with temperature and moisture. It's not passive. It's this dynamic struggle builders have always dealt with to keep things stable and comfortable. Sources like Understanding Wood and Fundamentals of Residential Construction really illustrate this. Take wood. It expands and contracts by significant amounts in response to changes in humidity.
Right, like wooden doors sticking in the summer.
Exactly. That's it, in action. And it's not just annoying, it causes cracking plaster, sticking doors, and buckling floors. So maintaining a stable indoor environment isn't just for us humans. It's vital for the building itself, for its structure, its longevity. The material is always trying to reach equilibrium with the air around it.
So the building is constantly fighting the environment. It sounds like a non-stop negotiation. But did builders always get why this happened? Or was it just seen as, bad luck or poor work if your floor buckled?
That's a great point. For a very long time, a lot of these issues were just accepted or blamed on bad wood or shoddy construction. The deep scientific understanding of why wood warps or plaster cracks came much, much later. But it's exactly those problems, the sticking doors, the cracked walls, that eventually pushed builders and scientists towards needing a more quantifiable scientific way to understand how materials behave. We had to start measuring and predicting, not just reacting. And that push for precision led to specific scientific measurements. We start seeing terms like dry bulb temperature and wet bulb temperature crop up in the sources.
Okay, break those down for us. Dry bulb is just regular temperature.
Yep, dry bulb temperature is just the air temperature measured by a standard thermometer, what your weather app usually tells you. Wet bulb temperature, though, is measured with a thermometer that has a wet sock or wick around its bulb. As water evaporates from the wick, it cools the bulb.
Okay, so why measure that?
Because the difference between the dry bulb and wet bulb temperatures tells you about the air's humidity. The more evaporation happens, meaning drier air, the lower the wet bulb reading will be compared to the dry bulb. A smaller difference means the air is more humid, less evaporation can happen. So using both gives you a much clearer picture of the air's properties. It's crucial for human comfort. Humidity massively affects how hot or cold we feel. And it's also critical for understanding how materials like wood will dry or how quickly moisture will evaporate from any surface. It moved us towards quantifying the air itself. And think about wood drying. It's not simple. The source explains how the outside layer, the shell, tries to shrink as it loses moisture. But the inside, the core, is still damp and swollen, so it resists shrinking.
Okay, so tension builds up.
Exactly. You get tension perpendicular to the grain in that outer shell, which can cause those visible cracks or surface checks. Meanwhile, the shell squeezing inwards puts the core under compression. This can actually cause the wood cells inside to buckle, which is called collapse, and that severely warps the board. It's this incredibly complex internal stress dynamic. It just highlights how much is going on even within a single piece of lumber. Every material has its own thermodynamic dance with the environment. Understanding that is key to building things that last and stay comfortable.
That's fascinatingly detailed, the internal battle inside the wood. And it's not just wood, right? How do newer manufactured materials fit into this thermal picture?
Right, even things we think of as modern, like light-gauge steel joists, have their own thermal story.
Yeah.
Steel is great structurally light, strong, stable dimensions. But it conducts more heat and requires more energy to process and manufacture.
Conducts more heat, so it lets heat pass through easily.
Yeah, it's a thermal bridge. Heat flows through steel much more easily than through wood or insulation. So, in winter, heat escapes through the steel framing. In summer, heat comes in. That makes your heating or cooling system work harder.
So it's a trade-off. Good structure, but potentially worse for energy bills.
Exactly. It's always a balancing act. Structure, cost, energy performance. The material choice, right down to the framing studs or joists, is already part of the climate control strategy, even before you install an HVAC unit.
Which leads us right into how modern construction really focuses on sealing buildings up tight, making those active systems work efficiently.
Precisely. Modern building science is heavily focused on creating a really well-sealed, well-insulated envelope. It's absolutely essential for efficient climate control. If your building is leaky, air and heat just pour in or out, and your HVAC system is constantly fighting a losing battle. The Builder's Guide to Hot, Dry, and Mixed Dry Climates gives tons of examples of these strategies. It shows a real shift from just fixing problems to designing proactively to prevent them. We're talking about detailed methods for moisture and thermal control, things like damp-proofing foundations to stop water wicking up from the ground, or putting down a 6 mil polyethylene ground cover as continuous vapor barrier in crawl spaces, making sure it runs up the walls and is sealed tight, blocking moisture right at the source.
Okay, so dealing with ground moisture first. What else?
Well, insulation is key, obviously. But there's detail there, too. Like, a thermal barrier must be installed over spray foam insulations in places like attics or crawl spaces. Spray foam is great insulation, but it often needs protection, maybe drywall or a special coating for fire safety, or sometimes just for durability and long-term performance. And for walls, you see things like rigid insulation, often with the joints taped or sealed to stop air leaks. Sometimes in brick veneer walls, they'll design an airspace vented top and bottom behind the brick.
Why vent behind the brick?
That allows any moisture that gets behind the brick to dry out, and it can also help dissipate heat in the summer. These aren't just minor tweaks, they're fundamental parts of creating a high-performance envelope that dramatically cuts down on heat flow.
It really is about creating this carefully controlled, multi-layered skin for the building, like putting it in a high-tech thermal suit.
That's a great way to put it. And roof insulation is just as vital. The roof gets hit hardest by the sun. So the guide mentions strategies like an unvented roof block enclosure for hot, dry places. You basically seal the attic completely to keep the insulated roof deck cool. In other climates, you might see continuous ridge insulation, wind baffle ventilation. That ensures good airflow through a vented attic to prevent heat buildup and condensation in winter. It's all about managing heat and moisture within the roof structure itself. And then there's the really specific use of different vapor retarders, Class 1, Class 2, Class 3.
Okay, what's the difference there?
It's about how much water vapor they let through. Class 1 is basically a vapor barrier. Like plastic sheeting, it blocks almost all moisture diffusion. Class 2 lets a little bit through, maybe used in more balanced climates. Class 3 lets even more through, used where you need the wall to be able to dry out easily in either direction. Choosing the right one and putting it in the right place in the wall or roof assembly is crucial. It stops moisture from getting trapped inside the structure where it can cause mold, rot, and ruin your installation's effectiveness. Without careful vapor control, even a super insulated wall can fail.
Wow. It's clear these details, they seem small, maybe overly technical, but they are absolutely critical. They determine how well the building performs on its own and how much work your heater or air conditioner actually has to do, how much energy it burns.
Exactly. And this deeper understanding of materials and these detailed construction techniques, they eventually pave the way for planning for mechanical systems within the building fabric right from the start. It wasn't just about passive anymore. The Kidder-Parker Architecture and Builder's Handbook from the early 20th century gives us a neat little glimpse of this. It casually mentions that if the thickness of wall is required for strength or to conceal plumbing or heating pipes, etc., 2x6 can be used.
So building thicker walls just to hide the pipes.
Right. It shows that heating pipes weren't an afterthought anymore. They were being integrated into the structure, influencing basic decisions like framing dimensions. And even the choice of basic building blocks started considering thermal aspects. Kidder-Parker notes that cinder concrete blocks have good sound and heat insulation properties. So builders were actively selecting materials partly for their inherent ability to keep the inside quieter and more thermally stable. It was setting the stage for active systems to work more efficiently inside a better performing shell.
So the foundation for modern HVAC was literally being built into the walls and floors, based on this growing knowledge of materials and the need to integrate these newfangled systems. A slow but really powerful shift.
That's right. A continuous evolution, really, in both thinking and practice. laying all the essential groundwork for what came next.
And what came next was, well, truly revolutionary. We've gone from the building being the climate control to engineering its fabric precisely. But now we hit this pivotal moment when climate control shifts again. It becomes less about passive design alone and more about active engineered systems, driven by new needs, new tech, and eventually even by law.
This is definitely where we see things like ventilation becoming formalized in building codes. And the drivers were a mix of things: health concerns, safety, and increasingly energy efficiency. Building Codes Illustrated really highlights this shift. For example, it mentions Ventilation Section 1202, which deals with ventilating hidden spaces like attics, but also crucially occupied spaces. The code starts addressing the air people actually breathe inside, recognizing indoor air quality as a public health issue. And here's a key insight from the codes. Where houses are found to be relatively airtight, the dwelling must be ventilated by mechanical means. That's a huge change.
Wait, so if you build a house too well sealed, you have to put in mechanical ventilation.
Pretty much. Traditionally, buildings were leaky. They breathe naturally through all the little gaps and cracks. Codes used to say if a house had 5 or more air changes per hour, meaning the whole volume of air inside swapped out 5 times an hour just through leakage, then natural ventilation was okay. But modern energy codes, like the IECC, they often limit houses to fewer than 5 air changes per hour to save energy.
So what does this all mean? If you build a modern, tight, energy-efficient house, which is what the codes want for energy saving, you're almost guaranteed to need mechanical ventilation, it seems. Paradoxical.
It is a bit paradoxical, isn't it? The trend is clear. As houses become more energy efficient and thus more airtight, it will become more likely that mechanical ventilation will be required more often. They even mention blower door tests becoming more common for homes.
What's a blower door test?
It's where they mount a big fan in an exterior doorway, seal everything else up, and either pressurize or depressurize the house to precisely measure how leaky or airtight it is. So, yeah, there's this direct link. We make buildings super airtight to save energy by stopping uncontrolled leaks, but that airtightness traps indoor pollutants and moisture. So mechanical ventilation systems have to come in to provide fresh air in a controlled way, ideally recovering some heat in the process to keep the indoor environment healthy while still being energy efficient.
Huh. It's that classic engineering thing, isn't it? Solve one problem, create a new one that needs an even smarter solution. Energy efficiency basically mandated the need for these mechanical systems, made them essential, not just a luxury.
That's a perfect way to put it. And this is where forced air heating cooling really takes over, especially in houses. It offers a way to handle heating, cooling, and that mandatory ventilation all through one system of ducts. Fundamentals of Residential Construction points to this, listing forced air heating cooling as a key system. Unlike older radiant systems, forced air can heat, cool, filter, and dehumidify. It's a more complete climate package. And builders got creative adapting existing spaces, like the idea of a crawlspace plenum. Instead of running ducts everywhere under the floor, the entire sealed crawlspace is used in effect as a giant supply duct for heating and cooling. Air is just pumped into the crawlspace and finds its way up through floor registers.
That sounds clever, but maybe a bit dusty. Did using crawl spaces like that cause new issues, like distributing dust or making maintenance harder? Or was it just accepted?
That's a really sharp question. And yes, absolutely, early crawlspace plenums had challenges. Keeping them perfectly sealed from ground moisture, preventing dust or smells from getting into the air, ensuring good air quality overall. Over time, codes and best practices got much stricter. They started requiring better sealing, insulation within the crawlspace, specific vapor barriers, sometimes even conditioning the crawlspace air slightly. It's a perfect example of innovation needing refinement to iron out the kinks. A constant learning process.
Right. It really shows these mechanical systems weren't just about being warm or cool anymore. They were about providing, as Le Corbusier put it, a minimum of comfort in these growing cities where just opening a window wasn't always enough or the air wasn't clean. Corbusier's idea towards a new architecture, that buildings should be a machine for living in or a tool, that's powerful. He argued entire cities have to be constructed or reconstructed in order to provide a minimum of comfort. It wasn't just about grand design, it was recognizing a basic need in an industrial age, and his point that the problem is in the hands of the technical expert. We must enlist the discoveries made in industry and change our attitude altogether. That just perfectly nails this shift. Embracing engineered solutions, moving beyond only passive methods, a call for architects and engineers to work together.
That quote is incredibly insightful, isn't it? Captures that exact moment. Architecture really started integrating industrial tech as part of its core mission. And with these systems getting more complex, more integrated, making sure they actually work right becomes a huge deal. Which brings us to commissioning in modern construction. The CMA Construction Management Standards of Practice define it as the startup, calibration, and certification of a facility.
So not just installing it, but proving it works.
Exactly. HVAC systems, electrical, plumbing, fire safety, they don't just get put in and switched on. They go through rigorous testing, calibration, validation by specialists. Does it perform how the engineer designed it? Does it meet the owner's needs? It's not just a final check. It's a critical process to ensure you get the comfort, the efficiency, the reliability you paid for. It's about making sure all that complex engineering actually delivers in the real world.
So you have to tune it like a precision instrument.
Yeah.
It really shows how complex modern climate control is and how far we've come from just, building a fire or opening a window, always chasing that optimal performance.
Precisely. Always chasing optimal performance, making sure all the pieces work together efficiently.
And now we're in the digital age, which is totally transforming how we design these systems, how we manage them, even how we interact with our own indoor climate. Buildings are becoming less like static boxes and more like intelligent, responsive things.
Yeah, this shift is massively driven by tools like BIM building information modeling. The BIM handbook really lays out how pivotal this is. It's not just digital drafting. It's about creating this rich 3D model packed with data about every single component of the building. BIM platforms let you manage the data within a model for different uses, and they specifically focus on functional performance and energy and environmental impacts. This enables what's called performance-based design.
Performance-based design, meaning you design based on how it will actually perform, not just following rules.
Exactly. Instead of just relying on standard practices or prescriptive codes, you can simulate and predict how the building will actually perform environmentally. Energy use, occupant comfort, daylight, ventilation. You can test all that virtually before you build anything. It allows for so much optimization early on.
So architects and engineers can run these complex what-if scenarios in the computer, tweak the design, see the impact on energy use or comfort, all before spending a dime on construction. That sounds incredibly powerful.
It is. And BIM helps manage the complexity too. It facilitates MEP coordination, mechanical, electrical, plumbing, integrating those complex HVAC systems, pipes, wires. It's crucial. In the old 2D drawing world, you'd often find out on site that a big duct clashes with a structural beam or a major pipe run. Big delays, costly fixes. With BIM, you can spot and resolve those clashes digitally in the model, saving huge amounts of time and money and making sure the systems fit and work properly. And then there's parametric modeling. This is really smart. It means elements in the BIM model have relationships. If you change one thing, like a window size, the model automatically updates related things, the wall area, the structural load, maybe even the calculated heat gain for that zone.
Whoa, so it recalculates automatically.
Yep. Shapes and designs can be automatically reevaluated and rebuilt based on changing parameters. So you can rapidly test design changes and instantly see the impact on performance. It makes optimizing for environmental factors incredibly dynamic and fast compared to the old way.
Okay, here's where it gets really interesting again. BIM isn't just drawing. It's analyzing, predicting, optimizing how the building interacts with the environment and the people inside it. It's taking design into a much more scientific, data-heavy realm, light years beyond Palladio's intuition, really.
And that data-driven design flows right into using smart technologies and sensors in the finished building, taking climate control from static programs to truly dynamic, responsive environments. The city of tomorrow, sensors, networks, hackers, and the future of urban life gives us a glimpse of this. It talks about how sensor networks can transform buildings into intelligent agents with the capacity to learn from and coexist with their occupants. That's the vision. Adaptive HVAC.
Learning from occupants.
Imagine a system that doesn't just follow a timer. It uses sensors to know if you're actually in the room, maybe learns your preferred temperature for that time of day, detects if one corner is warmer than another, and adjusts airflow or temperature just for that spot in real time, based on actual use and maybe even direct feedback, not just presets. It learns patterns, anticipates needs, optimizes energy use constantly. The bigger idea is that integrating digital elements will allow the built environment to become a connective tissue between the realities of bits and atoms, an interface that enables spatial cybernetics.
Spatial cybernetics sounds fancy. What's that mean practically?
It means our HVAC systems won't be isolated. There'll be nodes in a network, communicating with sensors, with occupants via apps, with building management systems, maybe even with the energy grid itself. This interconnectedness allows for incredible levels of efficiency and customization.
And we see bits of this already, right? Connecting our home heating systems to our smartphones, being able to adjust the thermostat from work or check energy use. That was science fiction not long ago.
Exactly. And it scales up. The source mentions things like a global energy grid and overall energy use. The idea is that our smart buildings, with their optimized climate control, eventually plug into a larger, smarter energy ecosystem, balancing energy demand and supply across huge areas, integrating renewables more effectively. Individual comfort connects to planetary sustainability.
So this tech push isn't just for convenience. It lines up with these bigger goals of saving resources, being more sustainable, which we see reflected in the building industry too, right? With things like green building certifications.
Absolutely. The CMAA Construction Management Standards of Practice specifically mentions projects aiming for LEED or Green Globe certified status.
Yeah.
These programs heavily reward buildings that cut their environmental impact. And smart, efficient HVAC is a huge part of scoring well on those certifications. It drives innovation in climate control tech. But while this tech offers amazing possibilities, we also need to think critically. The existential pleasures of engineering offers a really important caution. Beware of slogans. And it reminds us that technology is not an independent force, but an activity in which people engage because they choose to do so.
Meaning technology doesn't just happen to us, we choose to use it, and how.
Precisely. It's a vital reality check against thinking technology alone will solve everything. Human choices, our values, our priorities, they still shape how we apply this tech, especially around energy use, privacy, our whole relationship with our environment. We decide how smart we want our buildings to be, how much data they collect, how we interact with them. It's not inevitable. It's a path we are actively choosing. We need to make sure the tech serves real human needs and sustainability, not just, tech for tech's sake.
That's a really crucial point. It brings it right back to us, the people living and working in these buildings. What new possibilities, sure, but also what new responsibilities come with this level of climate control? Are we just becoming consumers of perfect comfort, demanding 72 degrees year-round? Or can we be active participants in this bigger system, making conscious choices about our comfort and what it costs environmentally and maybe otherwise?
Wow, what a sweep through history today. From those ancient builders, so clever with passive techniques, understanding sun and wind and materials, all the way to these complex, data-driven, almost living systems we're developing now. Our long quest for comfort has literally reshaped our world.
It really has. It just reaffirms that the story of HVC, it's fundamentally a story about us, humanity constantly trying to shape our surroundings. For comfort, yes. For productivity, definitely. And now, increasingly, for sustainability, too. Just this ongoing testament to our ingenuity, always adapting to the environment, always pushing what's possible inside our buildings. And it's a good reminder, isn't it? Every single building, ancient or brand new, is kind of an ongoing experiment. An experiment in how to live comfortably and hopefully more responsibly within our environment. That dialogue between us and our buildings, it just keeps evolving, getting more complex, more intimate.
It really does. And, as our buildings do become these intelligent agents, learning from us, maybe even anticipating our needs, what new expectations will we start to have? What will we demand from them in terms of comfort? And maybe more profoundly, what new trade-offs, what new compromises perhaps around our own adaptability or privacy or the ultimate energy cost will we find ourselves making in this never-ending search for that perfect indoor climate? Something to think about next time your smart thermostat quietly makes an adjustment, maybe learning just a little bit more about you in the process.